So manual selection of corresponding points. MATLAB selection of, let's say, ground control or control correspondent point, however way you want to do it, images. The closest would come control point selection tool. You go there. Again, if you want to make sure that this is the case, you just scroll down, see what the image looks like. Oh, this is what I want. Okay. You then go copy it. You have the moving and fixed, meaning which one is going to move towards the other one in terms of the registration. Just go paste that there. So the moving is typically going to be our. So then what you do is you basically have some tools on the top here with respect to the zoom and with respect to the moving it around. And then here is where you basically have to select the corresponding points. So you want to, let's say, find the correspondence between this point and this point. So you go to that selection that is there, and you go there as close as possible and select one there, and then select another one there too. Again, you select whatever point correspondences that you think are similar, play around with it. So basically get the control points. Again, if we have at least 5, we can get a good one. We would like an overdetermined system and as much as possible diversity in our groups. So basically we take a look at them. You have even more, 8, 9, 10. And I think at the end, I proposed about 13 or 14, 12, I believe, sorry, that we looked into. And that was how you can go around and do that. We have to export this. So you go and you go to the file for all of these points, and you press export. Basically, the first one is your BIM. The second one is the other one. You can basically perform that. This is BIM, because that's the first one that we identify. This is the actual. I just put it BIM underline P, an actual or reality underline P, however way we want to look into this. And then press enter. And then if we go out of here, we're going to see that we have a 12 by 2. So 12 is the number of points, and then 2 is basically the X in pixels and then the Y in pixels. So as simple as that. And every point, basically every row in BIM P and in actual P correspond together based on how we selected first one from that and then another one from the other one. Okay. So imagine now I want to show these matches the way that I did it for this particular lecture. Again, show point matches, MATLAB. Display corresponding feature points. So this is the function. Again, you can scroll down to see how this looks like as well. If, let's say, you're searching for a function that we didn't discuss and you want to see how it looks, just go and paste that there. I1, I2, and the match point. So I1 is, let's say, our A, which was our reality. Let's say we want to do it that way. And then B, and the second one, B is our BIM. So the matching points should now be the actual underline P. Yeah, we just copy it from there. And then the BIM underline P, right? So you just press enter. So it would basically superimpose it on top of each other. Now, if you want to do it side by side, now you have to go and take a look at how MATLAB does that overall. So if you go and you see, for instance, there's method there, okay? You can go and take a look at the method, and it says, see, you can blend it together. You can also montage it together, meaning side by side. So this is the original method, but I want to do it side by side. So I just copy this montage there. So the default is the other one. It wasn't the montage. So you just do that, and then in your basic quotation, you press montage, and then you enter, and then you see exactly this, where the point correspondences are showing just as a visualization tool. So now we have the point correspondences. What is next is to find our essential matrix, right? So given some parameters, let's say your calibration parameters, your focal length, your principal points, how can we get the essential matrix? Again, the exact same process. I have no idea. How do you get essential matrix? Essential matrix, estimating essential matrix, MATLAB. Enter it. Estimate essential matrix from corresponding points, a pair. So what it requires is here, it has matched points 1, match point 2, and camera parameters. What is camera parameters? So you just click on the camera parameters there so that it could give you some ideas on what it is. And it takes you there. So it says camera parameters or camera intrinsics. Let's click on this to see how it looks. So you go, and it says, oh, this is the same focal point, principal point, image size. And oh, this is the exact same thing that we were talking about here, that for the essential matrix, we need the point correspondences and we need the basic parameters that we have. So focal length, the focal length is F is 2000. Principal point is 670 and 502. And the image size, we have the image size there. Okay, so let's just copy this into our MATLAB. Paste it. So let's just change this to K. Focal length, we'll just put the 2000 because we assume that we know this. Principal point, well, it's the 670. That's the X direction, and the Y direction afterwards. Again, if you have any concerns with that, you can always go to the full documentation of a lot of these that are built-in MATLAB functions. Then we're going to talk about if we want to build MATLAB function, how easy that is as well. But let's get first familiar and comfortable with it, and then we can take it from there. Then the image size is basically how we see it here, the row and the column. So it's 1005 and 1341. Then we basically close that, and this is how we basically introduce a vector as well. So if we have the brackets and a comma, this is going to be a row vector. If we have a bracket and semicolon and the other one instead of the comma, it's going to be an actual vector. It's going to be a column vector. But for row vectors is enough. And a lot of these built-in functions, they basically, if there's only a vector, regardless of the direction, it will still, as long as the size is right, meaning we have 2, it would still automatically identify that. But just so you know, this is how we also represent columns and rows. So the K matrix, we just put that there. It gives you a structure of intrinsic parameters. The reason why we did this, we can do all of the computations that we have talked about and create functions in MATLAB ourselves. However, MATLAB has all of this information. So let's go with how MATLAB says, and let's see what we're going to get at the end. So the next one is, again, going back to the essential matrix. Now that we have the camera parameters, oh, we have the match points as well. So you just copy that. There's nothing else that we need. We go and we paste it here, and we go to match points 1. That is what? That is, for instance, our BIM or the actual dependent upon which one we want to put on the other one. This time I decided that I want the BIM to be my center so that the other one would be adjusted towards that. Second one is your actual. Let's paste that there. And then the camera parameters, you just put K there because that's what we did there. Okay. And here, of course, the alphabet and the uppercase and lowercase actually does matter. So this is our essential matrix. This is what we get as the essential matrix. Now we have the essential matrix. How do we get position from and orientation from the essential matrix? So this was how it was. Calculation-wise, it's just a singular value decomposition, and there are various methods to do that. MATLAB uses their own, not their own, someone's method on using, what is it called, robust statistical methods to extract the E matrix, and then from that, basically, how do you get that? So estimated camera pose from essential matrix, MATLAB. So, compute relative rotation and translation between cameras. Okay, we do that as well. What does it require? M. What is M? It says here that M is, before we go there, here M is fundamental, essential, or homography matrix. Homography is between two cameras. If you have a plane in the real world, that plane and the pixels that represent that plane in both of these cameras, both of these images, from one to another can be projected as a homography, which is a 3x3 matrix. That's what a homography is. So every plane would be represented, or every pixel on a plane would be represented in real world, would be represented by homography between two images. Fundamental matrix would provide you with the basic what is it called, the epipolar geometry, and then the essential matrix would provide you with, given your camera parameters, you can get the orientation and rotation. So the M is there, the camera parameters is K, the inlier points is basically the actual point or whatnot, and then from that we basically copy this function, take it there. We just put R as our relative rotation, and the relative location we put it as T, just to change variables to be consistent with what we've talked about. Just put E there, camera parameters as K, inlier point 1, that's again the same BIM underline P. However, I'll tell you this, that's MATLAB, because they do the essential matrix using robust statistics, it might take some of these points away, which I'm going to show you in the next slide as well, just to have some idea of, you know, when you see a function and you see some sort of difference there, you have to sometimes go into it and see how it's calculating. Get the rotation and translation. So now we take a look at the rotation matrix. There's a rotation matrix, and then the translation matrix. There's a translation matrix. The translation vector, I apologize. So now we have the relative orientation between that image and the other image, given some point correspondences. Using MATLAB, we can calculate that accurately. Let's see how we can plot those cameras the way that I plotted. Okay. So again, our friend Google, we go there, we say basically plotting cameras, MATLAB. Plot a camera in 3D coordinates. And it gives you this function as well, plot camera table. Let's see what a camera table is. And you're like, oh, you can actually have, if you have R and T, and if you take just a look at the examples here, and this is very beneficial because whatever you want to actually do, you can take a look at the examples, at least the function that there is, and provides you with good examples there. Well, if you have the rotation translation, you can estimate the pose using rigid 3D. And then after that, you can basically put plot camera, absolute pose, which is basically the rigid 3D, and it will provide you with a pose of that. Okay, so we'll just do that then. We first go to the pose, copy this, and then copy the other one. So copy this, paste this here. So we can change this to our, for instance, pose actual, because the rotation and translation was relative to from the BIM, and then the BIM, because of the relative orientation, if you remember, one would be I and 0. I is a 3x3 matrix, right? So if we want to do the same thing with the BIM, the rotation would be the I matrix, which is the identity matrix, is a 3x3 identity matrix, and the other one would be a 1x3 vector of 0, 0, zeros. So in order to do that, MATLAB has a function for the identity matrix. It's basically I, and then the basically number of rows and columns. So I, 3, and 3 would be a 3x3 identity matrix. Okay, and then that would be a 0, 0, 0. You can use it this way. MATLAB also has a function for how to define a set of zeros. You can say 0, zeros, parentheses, for instance, 3 and 1. That means that it would give you a 3x1 vector for zeros, and in this case it has to be a 1x3. So you can, instead of saying a bracket 0 and 0 and 0 close bracket, you can also do this in a summarized way with zeros, parentheses, 1, comma, 3, close parentheses. Okay, so it gives you the pose. Now you have the two poses, the way that MATLAB's function works. Now let's go back and see, okay, what about the camera plot function? Okay, let's just copy this. The opticity, it doesn't matter too much for me. I'm just gonna leave it the way that it is. So let's say camera underline actual, then absolute pose, sure. And now we have to change it to the pose of the actual, right? So it's pose underline actual. Then you open it up and it looks like this. So if you now want to plot the second one on top of this, you just have to put the hold function. Again, these are certain things that you get familiar. You can always, again, Google this. How do I hold a figure in MATLAB? You would be able to do that. But while you go forward and while you play around with it, you're going to learn quite a bit about some of the built-in function. And then hopefully you would be starting to create new as well. And these are the two basically images. Now, when I zoom it in, it looks bad. So again, I want to make the axes the same. You just put axes equal. Again, you can Google this. How do you create similar axes in the figure in MATLAB? Now, the units of these axes are the same, meaning that 1 unit in the x-axis is similar to 1 unit in the y-axis and is similar to 1 unit in the z-axis. That means that it doesn't stretch out or stretch in. Okay, so the last thing that I wanted to talk to you about was the understanding this function. So if you take a look at it, sometimes you're going to see that that these two are not going to look as good. Like, this doesn't look like the image was taken that farther away. Why is it giving me that in my relative orientation? So for that, you have to go and take a look at how MATLAB is estimating your essential matrix. So it talks about the inlier index. That by itself is alarming. That means that certain points were considered as outliers or potentially considered as outliers. So what it does is it uses this M estimator. This is how it uses it. That's why for functions that you're not so familiar with, and that's why I actually brought this over, is that if you're not that familiar with the function, it's good to review what it's about, how it's actually calculating. On the bottom, almost always it provides you with a good level of referencing as well, so that you can take a look at where that calculation comes from if you ever want to go back and take a look at it. but it's very important for us to see it because if we get bad results, it's not really the function's fault. We have to know what the function is about and why that function was not working correctly, or why that function was removing some of the points, so it created that much of a disparity. So it says it uses the M estimator sample consensus, which is basically M estimator is a robust statistical method. Random sample consensus is a computer vision Monte Carlo based method. You basically utilize those two together to do that. So this is where that distance function really is, and this is the maximum distance. This is called the Samsung distance. I'm not going to go into too much detail about the Samsung distance, but what it is typically, and it just for some reason was named after this person, because this person, Samsung, in the I think late 80s even used this for an ellipse detection, an ellipse fitting method for residual. And that is, it's basically the algebraic function divided by the gradient of that function. This is something well known for algebraic functions that for quadratics that are quite adverse to gradient change. So that's what it means. But what it means in a crude way, that what we can be utilizing it for, is that probably the 0.1 is very, very small. So we have to increase that. So let's go and basically do the essential matrix again. We just press the up button, it brings us the same one, and then you do E2, and this time you basically can change what that particular was. So you can say max distance, and copy that, and you can increase that. And then now this time I want to also see what it brings about with respect to the original one as well. So what I do is, this 0.1 was the original one, right? This was the default. So if I remove all of these, and if I do, let's say 100, this is going to provide me, or 1,000, this is going to be providing with a different one. So let's go with the default, and let's see what the inlier points are in. And let's press enter. So now the E2 is going to be the same as the E, as you can see here. And the inlier points now says that which points were not, or which point IDs were not considered by means of the Samsung distance being 0.1. Now, if we increase this to, let's say, 1,000, let's put in layer 2, and you enter that. Now, this time, in layer 1 will obviously the same, but in layer 2 now has all of the points. Instead of point ID 1, 4, 6, 7, and 10, that were not considered in the estimation of your essential matrix, now all of the points are estimated and measured. And from that, you can then do the recalculation and see how it is, and see if there's any type of distance. And there's a significant difference between these two as well. Like this is 0.4 and this is 0.29. So it's quite a significant difference. And this is because when you get only a particular number of points and you have an overdetermined system, it would give you a better understanding of what the mean is. Again, I can't stress that enough. So you basically perform the same one, and this time you do it by means of E2, which has considered all of the points. I'll just remove that, enter that. And now this time you get a better view that is closer together, that is more synonymous with what you're about to say. Again, it's not going to be as accurate regardless. Why? Because we have only limited number of points. Now, if we do it with 23 points instead of these 12 points, and points that have more similarity in the bottom and other geometry of that area, it would provide you with even more opportunities and better results.